Okay, folks, today we have another treat especial. I feel like the keynotes have all been fantastic. So Işıl's going to be giving the final keynote here at PLDI. I remember I first learned of Işıl when she was giving a job talk at UC San Diego, and there's a whole thing about abduction. I thought it was some kind of like exercise or something for your core. And today we're learning about another fancy word, neurosymbolic reasoning. I feel like every time Işıl gives a talk, I walk away feeling very enlightened. So building on the stuff we learned from Sunho yesterday, I think we're in for a real treat. Işıl is, as you all saw, won the Reynolds Research Award last night, has been a true guiding light in the community, not just incredibly productive in research, but her students have all gone on to do amazing things. So I think just across the board, a fantastic member of the community. So Işıl, please take it away.
Thank you so much, Zach. Thanks, everyone. It's a great pleasure to be here. So as Zach said, my name is Işıl Dillig. I'm a professor at UT Austin, where I'm very fortunate to lead a wonderful research group called Utopia. And today I'm going to tell you about some of the work that we've been doing on the topic of neurosymbolic program synthesis. And I'll try to highlight in this talk how this field can help bridge perception and reasoning for many real-world applications. So first of all, to set the stage for this talk, I want to quickly go over two different learning paradigms that have emerged over the last several decades. So as you all know, one of these learning paradigms is, of course, deep learning, which has had a profound influence on computer vision and natural language processing, as well as many other areas outside of computer science recently, for example, in the natural sciences. Oops, sorry. This does not seem to be working. All right, let's see. Let me retry this. Give me 1 second. All right. Hopefully that won't happen again. I don't know what happened. Okay. But there's also another learning paradigm that has received an enormous amount of attention in the programming languages community, and this is, of course, program synthesis. And the goal of program synthesis is to automatically generate programs from some high-level expression of user intent. For example, it could be input-output examples, or it could be logical specifications. And program synthesis, as many of you know, has found numerous applications in the context of software engineering, data science, spreadsheet automation, and so on. Now, I would argue that despite the different use cases of these methods, deep learning and program synthesis are actually in some ways very complementary to one another. So in particular, if you think about the strengths of deep learning and deep neural networks, I would argue that where they really shine is their flexibility and their ability to handle messy, ambiguous real-world data like videos, images, and so on. On the other hand, if you think about their shortcomings, they tend to be fairly data hungry, right? They typically require large amounts of labeled input in order to learn something useful. And perhaps even more importantly, they're not very interpretable, right? It's very difficult to stare at the weights of a trained neural network and say, aha, I know exactly what this network has actually learned. And on a related note, not only are they uninterpretable, but they also turn out to be extremely difficult to verify despite several attempts from this community. It's not, verification doesn't scale, and it's very difficult to prove properties about deep neural networks. On the other hand, if we think about programmatic representations and program synthesis, we see a very different profile. So I would say that their biggest advantage is interpretability. So it's much easier to inspect a program and understand what it is doing. And also, on a related note, they're also much easier to verify thanks to decades of research in the formal methods and programming languages communities. And I would also argue that a lot of recent research in programming languages has shown that it's possible to learn programmatic representations in a way that's not very, very data hungry. On the other hand, in terms of their weaknesses, programmatic representations in program synthesis is not very good at dealing with ambiguous, messy data. Okay? So this brings me to the central question of this talk, which is how do we combine these two learning paradigms into a unified approach that can tackle real-world problems much more effectively than either approach can on their own. So this is precisely the point of neurosymbolic learning. So the idea here is we want to try to get the best of both worlds by using neural components for perception or perception-like tasks, but at the same time, we would like to combine them with programmatic representations in order to do better logical reasoning and algorithmic manipulation. And in a nutshell, by using neural components, we get the ability to handle complex unstructured inputs, but at the same time, by combining them with programmatic representations, we get composability, we get modularity, and importantly, we also get greater interpretability as well as more data-efficient learning. Okay. So with that background, here's a quick outline for the rest of the talk. So this talk roughly has 5 segments. So in the first part, I'm going to introduce the general neurosymbolic learning framework that both my group and several others have been advocating for. And then in the next part, we're going to look at different instantiations of this framework for several real-world applications. One of them is going to involve images, namely image search and editing. Then we're going to take a look at an application that involves text. We're going to talk about data extraction, and I'm also briefly going to talk about an application in robotics. And then in the final part of the talk, I'll tell you about some ongoing work that we have on ensuring trust in the neurosymbolic setting. Okay, so first, let's start with the general neurosymbolic learning framework. So in my view, whenever we talk about a learning framework, there are 2 important questions that we need to answer. And the first question is, what is the representation? In other words, what is the thing, the shape of the thing that we're actually trying to learn? And then once we settle on the representation, there's the equally important question of what is our learning algorithm? What are the methods that we use in order to learn this desired representation? So let's briefly talk about both in the context of neurosymbolic program synthesis. So as its name indicates, the representation here is going to, of course, blend neural networks with symbolic traditional programming language constructs. And in more detail, the representation is typically going to be a program that's expressed in a domain-specific language rather than often a general purpose language. And you typically choose a DSL in order to achieve a good trade-off between expressiveness within that domain, but also being amenable to few-shot learning. Okay. All right, so since our DSL is neurosymbolic, of course, it's going to have some neural primitives. And as I was saying earlier, these neural primitives are often going to be used for perception. And for the purposes of this talk, all of these neural primitives are going to correspond to pre-trained neural networks. Okay? So for example, to be concrete, if we have a domain-specific language where the input is images, here you might have neural primitives that are used for doing things like image segmentation or object classification. And ultimately, these neural primitives allow us to take some raw set of pixels, a raw image, and then allow us to parse it to a more symbolic representation like a scene graph, where you have a notion of objects and where each object has various attributes associated with it. So for example, like you have an object type, that's a face, it has a certain ID, and various attributes like whether it's smiling or not, and so on. So in general, these neural primitives in our language will be crucial for taking some high-dimensional unstructured inputs and parsing it to a symbolic representation that is amenable to programmatic manipulation. Now, of course, since we're dealing with programming languages, we're also, of course, going to have more traditional programming language constructs like conditionals, loops, as well as several task-specific abstractions, for instance, fold or filter. And importantly, I do want to note that we don't prescribe any particular programming paradigm here. Our DSL could be imperative, it could be functional, or it could be declarative. And in fact, in the rest of the talk, when we look at applications, you'll see all of these 3 different paradigms come up in different domains. Now, another point that I want to make here is that in terms of their syntax, the symbolic constructs and the neural components pretty much look, exactly the same. They often both look like just regular function calls. But in terms of their semantics, there is an important distinction. So in particular, the symbolic constructs have precisely defined semantics. So we know exactly what they do. They always produce the ground truth answer. On the other hand, the neural components, we don't know what their semantics are. They're like black boxes to us. And furthermore, as you will see later, which will play an important role, they can also have mispredictions. They don't always produce the ground truth answer. So we briefly talked about the representation. Now let's talk about the learning algorithms that we use in this context. So first, what are the goals of our learning algorithm? I would say that there are 2 important goals that we want to achieve here, and one of them is data efficiency, meaning that we would like to learn the desired program from very small amounts of user input. And this is important because in program synthesis, we typically want to customize a program for an individual user. And of course, it's not really realistic to expect them to provide a ton of labeled data because it's coming from just a single person. And this is precisely going back to what I was saying earlier. This is precisely why we typically deal with domain-specific languages here as opposed to general-purpose languages, because by having this DSL, we can essentially bake in sufficient inductive bias into the hypothesis space that in turn facilitates few-shot learning. Now, in addition to data efficiency, another important goal is that learning should be fast. And again, this is important because program synthesis is often used in interactive user-facing contexts. And in this context, of course, users don't want to wait for hours and often not even for minutes. Okay? So in order to achieve this goal, as you will see, we're going to be leveraging the formal semantics of our programming languages, at least of the symbolic constructs, in order to facilitate efficient learning. All right, so this brings me to an important point that I wanted to make about the learning algorithm. So recall that we have this representation that blends neural networks with symbolic constructs. And just like the representation, often the learning algorithms that we use also have this interplay between neural guidance and symbolic reasoning. And what do I mean by that? Well, at the core, program synthesis is a search problem. So at the core, we have some sort of backtracking search algorithm. But rather than doing blind search, we are going to be using various kinds of machine learning models, including LLMs, in order to guide the search for plausible programs based on the limited training data that we have. But equally importantly, we're going to leverage logical reasoning and program analysis in order to systematically prune large parts of the search space. As you will see, we will resort to techniques like a static type system or abstract interpretation in order to prove unrealizability of entire parts of our search space. Okay? So that was a quick overview of the learning framework. Now let's look at some concrete instantiations of this framework. And to get us started, I'm going to first talk about our work on image search and editing. And if you're interested and would like to learn more, this segment of the talk is based on our PLDI paper from 2 years ago, as well as some follow-up work at Chi-24. And this work was led by my student Celeste Barnaby. Okay. So let me give you a motivating scenario for what we're trying to do here. So let's say you have a large collection of images, and some of these images are relevant to what you're looking for, and others are not. So you want to search for the relevant subset of the images, and maybe for those that are relevant, you may also want to apply some selective edits. Okay, so concrete example. So let's say you have a bunch of photos from your childhood, and for whatever reason, you want to find all the images. that contain two of your friends sitting next to one another. Let's say these are Michelle and Greg. Let's say this is Michelle and this is Greg. And so that's the search aspect of the task. You want to find all the images where Michelle and Greg are next to each other in the image. And maybe also for privacy reasons, you may also want to edit this image. For example, you might want to blur the faces of everyone else except for your friends Michelle and Greg. So for instance, if this is our input image, we want to obtain this output, and we want to apply a similar transformation to all of the images in your collection. So I would contend that this kind of task is a perfect fit for neurosymbolic learning for a variety of reasons. So the first reason is that obviously there is a big need for using neural networks here because we need to do perception. We need to do facial recognition. We need to be able to answer the question, does this face belong to Michelle? Does this belong to Greg? And so on. But beyond just doing facial recognition, there is also some sort of basic logical reasoning aspect to this task. Namely, after detecting the faces, you need to reason about the spatial relationship between these objects. And for example, you want to answer the question, are these two objects adjacent to one another in the image? And last but not least, there is also, of course, a programmatic manipulation aspect to this task. Once you detect all the faces, you want to iterate over all of them, and you want to apply an action, in this case blur, to all the faces except for two specific people. Okay. So for these reasons, we took a neurosymbolic approach to these kinds of image search and editing tasks. And as usual, our starting point was to design a suitable domain-specific language. So you don't have to understand everything that's going on here, but at a high level, programs in this DSL allow us to extract a set of objects in the image using this non-terminal E, which I'm going to refer to as object extractor. And then you can apply various actions like blur, blackout, sharpen, and so on. Okay? And if you look at this non-terminal E for object extraction, one thing that I want to highlight here is we have a mix of symbolic constructs as well as neural components. So in particular, these constructs like complement, union, and so on are just, they have precisely defined semantics. They just correspond to regular set operations. On the other hand, we also have these constructs like find and filter, which do what you might expect them to do. But importantly, these predicates that are nested inside them are actually implemented using neural networks. So for example, you have a predicate face of n that's allowing us to do facial recognition where n is some identifier of a specific person, and object of O is doing object classification where O could be something like a face or a cat or a dog and so on, a certain type of object. And if we go back to our running example from earlier, this is how you may be able to express this task in our DSL. So basically, if you look at this highlighted part, this is extracting the part of the image that contain Michelle and Greg, but only if they are sitting next to one another. So in more detail, this find, the first instance of find, is extracting Michelle, but only if she's sitting next to Greg. And similarly, this one is doing the symmetric thing, but for Greg instead of Michelle. And then we take their union. And then what we do here is we take the complement of that region and intersect it with all of the faces, which ends up giving us all the faces except for Michelle and Greg. And finally, we can apply a specific action like blur, which gives us the desired output image. So that was a quick overview of our representation in this context. Now let's talk about the learning task and the learning algorithm. So here, in order to automate these image search and editing tasks, we take a standard programming by example approach. So the idea here is that the user provides a small number of labeled examples. So a few input images, and by few I mean hopefully less than 5. And also their corresponding output, whether that image is relevant, and if so, what is the desired edit. And then our goal here is to learn a program in this DSL that can be used to perform the desired task. So the question is, how do we do this in a way that is actually effective in practice? So for those of you who may not be familiar with program synthesis, before I talk about the specific ideas used in our method, I want to give a very brief background on program synthesis techniques. And first of all, there are many different program synthesis techniques, but one common algorithm is what people refer to as top-down enumerative search. So the idea here is that you have the notion of a partial program, and you can think of a partial program as an abstract syntax tree, where some nodes in this abstract syntax tree are annotated with concrete terminals in the grammar, like union, intersect, and so on. But some of the other nodes are annotated with non-terminals, meaning that they're currently unknown, and they can be instantiated with arbitrary expressions as the search progresses. Okay, I'm going to often refer to these unknowns as holes in the partial program. So the idea behind top-down enumerative search is that at every step you have a work list of these partial programs, and then at every step you dequeue some partial program in your work list. You can either do this using a heuristic like selecting the simplest program, or often you can also use some sort of machine learning guidance to do this. But in any case, you get a program, and then you choose one of these holes in the program, and you instantiate it, you expand it using the productions in the grammar, and you keep doing this until one of two things happens. So one possibility is that you have a complete program that's actually consistent with the user's specification, and if that happens, you often produce this as the output of the synthesis procedure. But in some cases, you may still have a partial program, but using various techniques, you can actually prove that this partial program is inconsistent with the specification. What I mean by that is you can construct a proof that there is no completion of this partial program that's going to satisfy the specification. So in that case, we refer to that program as infeasible or unrealizable. So a big part of program synthesis deals with the question, how do you detect these infeasible partial programs as early as possible within the search procedure? So this is precisely where the semantics, the formal semantics comes into play. And the idea here is that we would like to leverage the semantics of the symbolic constructs in the DSL in order to perform logical inference and prove unrealizability of certain parts of the search space. So let me just illustrate that with a concrete example in our image domain. So let's say that we are considering this partial program for the object extractor, where we committed to union being the top-level construct, but the operands of union are currently unknown. Okay, so that's indicated by these question marks. Now, also suppose that in the examples that are provided by the user, they're applying a blur action, but this blur action is only applied to faces, right? And even though there are many other types of objects in the image. Now, from the semantics of union, we know that it's going to preserve whatever object is extracted using its operands. So based on that, we can deductively infer that however we instantiate these holes, they must also only produce faces. If they produce something other than a face, then we know we must be on the wrong track, right? So therefore, if at any point we instantiate this hole with something like isCat that basically extracts all the cat objects, we know we are on the wrong path, and we can prune this partial program without even considering how to instantiate the second argument. So this is the idea behind how you use the formal semantics to do systematic pruning of the search space. Now, another important idea here is based on the observation that our hypothesis space is highly redundant. So what I mean by that is there are many programs in our hypothesis space that are actually observationally equivalent, at least on the examples provided by the user. Okay, and we would like to eliminate redundant parts of the search space and do some sort of symmetry breaking, if you will. So to illustrate what I mean by that, again, let me give a concrete example. So let's say we have this partial or complete program where we take the union of some expression E with all of the objects that have their eyes closed. This basically gives you all the faces where the people's eyes are closed. But now suppose that in the examples provided by the user, there are no faces that have their eyes closed, right? So in other words, this is just going to give us the empty set. And if you take the union of E with the empty set, well, that's obviously going to be observationally equivalent to whatever E produces. And since this entire partial program is equivalent to something much simpler that we likely explored before, there's no point in considering this duplicate program. So based on this, what our method does is that it uses a combination of partial evaluation and equational term rewriting to eliminate redundant parts of the search space. So that's all I wanted to say about the learning technique, and now let me give you some highlights from our evaluation. So we implemented this method in a tool that my student named ImageEye, and we used it to automate a diverse set of image editing tasks involving different type of photographs. And just to give you some idea, for example, we have this set of photos from a wedding, and you might want to, let's say, search only those photos that contain just the bride and the groom and no one else. And similarly, you may want, if you're given a bunch of photos of receipts, you may want to remove sensitive information, for example, phone numbers or credit card numbers and so on. So just to give you some ideas about the tasks. And what we found experimentally is that our tool was able to learn the desired program for 96% of these tasks, given a 2-minute time limit for synthesis. And furthermore, we found that it's quite data efficient. It requires 4 examples on average, so we think it's not too burdensome on the user. And also, in terms of the efficiency of synthesis, we found that it's practical enough to be used in interactive settings with a median learning time of around 1 second. Okay. So to recap, in this segment of the talk, we looked at an application of neurosymbolic programming in image search and editing. And by using neural components, we get the ability to do things like facial recognition, object classification, and so on. But at the same time, by combining these neural networks with programming language constructs, we get the ability to do some sort of logical reasoning over the detected objects and also programmatically manipulate images. Okay, so in this next application domain, I'm going to switch gears to a different modality of input, namely unstructured or at least semi-structured text. And we're going to talk about how you can do data extraction using neurosymbolic methods. And this part of the talk is based on our PLDI'25 paper, if you would like to learn more. And this was led by my former student, Jocelyn Chen. OK. So again, let me give you a motivating scenario for what we're trying to do here. So let's say you are on the job market and you have a bunch of job listings, for example, in the form of a big spreadsheet or a text file, and you want to filter all those job listings that are relevant to your particular search. For example, let's say you are interested in software engineering jobs in the US, so that's you only want to retain those listings. So just to give you an idea of what we're trying to do, if you have a spreadsheet that's full of entries like this one, clearly the first and the last one should be retained because .NET developer is a type of software engineer. Winter Park, Florida is in the United States. But the middle 2 should be filtered out because, for example, this is in Germany as opposed to the US, and paralegal is not a software engineer, and so on. So the question is, how do you do this data extraction task? Well, generally, when you want to do data extraction, one of the powerful tools that we have is regular expressions. So your first thought here might be, can I write a regular expression to do this? Unfortunately, if you think about it for a second, you'll realize that this is not a great fit for regexes. For example, how would you write a regex to match all the software engineering jobs, right? So for example, .NET developer, blah, 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 neither syntactically contains the word software, nor does it contain the word engineer. And similarly, how would you write a regex to match all of the US cities? Well, if you're very patient, you could maybe spend the whole afternoon hard coding the cities, but I think we can agree that this is not the best use of anyone's time. So this brings me to our approach, which is neurosymbolic. So in this work, we proposed a new neurosymbolic program abstraction that we call semantic regexes. And the idea behind semantic regexes is to extend regular expressions with LLM-based semantic reasoning. Okay, so in more detail, we're going to retain our traditional regexes, which we all love, in order to do syntactic pattern matching. But in addition, we're also going to augment it with large language models in order to do further semantic filtering over the match text. Okay. So in more detail, the idea here is rather than viewing a string as a sequence of raw characters, we're instead going to think of a string as a sequence of tokens where each token has some intrinsic meaning and various attributes associated with it. So for example, if I give you this string, from the perspective of a traditional regex, well, you would say this is the concatenation of a bunch of digits, a 2 followed by a bunch of zeros. But from a more semantic perspective, well, this is a string that represents a number, and that number has various properties, like it represents a positive number. It has the value 20,000 and so on. As another example, if I give you this string, AUSTIN, from the perspective of a traditional regex, you would say, well, it starts with a capital A followed by a bunch of lowercase letters. But if I asked any of you in the audience, you would say, well, that's a string that represents a city. And again, this city has various properties like being located in Texas, United States, and so on. And as a last example, if I give you these two strings, from the perspective of a traditional regex, the only commonality between these words is that there are two words that start with a capital letter and that are separated by a space. But if I asked any of you in the audience, you would say, these are celebrity person names, right? So we basically capture this using this notation that looks exactly like a refinement type. And in the context of semantic regexes, each atom has a base type associated with it, like a number or a city. And you can also have an optional logical qualifier. So it's a logical formula that allows you to further filter the match text. So for example, here, if you look at the second regex, it's telling us that whatever string that we match should correspond to a city. But we don't want just any city. We want a city whose corresponding state is, for example, Texas. Okay. So that's the syntax. Let's talk about the semantics. How do you evaluate them? In other words, if I give you a semantic regex and a string, how do you decide whether there's a match or not? So the evaluation of semantic regexes is going to be neurosymbolic. And specifically for the base type, we're going to consult an LLM and ask the LLM, does this string represent whatever, does this represent X, where X is the type like a city or person and so on. Okay? And if the LLM says no, then we say there is no match. Otherwise, we're going to proceed to evaluate the logical qualifier. And in order to do that, we're first going to do some sort of retrieval. So we're going to consult an external knowledge base, or this could also be a large language model. But we're going to extract the required attributes of that type. And this will allow us to parse this string as an object of the suitable type. And once we have that, we can symbolically evaluate our predicate. And based on that, if it evaluates to true, we say there is a match, and otherwise, no match. So going back to our earlier example, recall that we wanted to write a regex that can match all software engineer job listings in the United States. Now that we have these semantic regexes, we can achieve this task by writing a regex that looks like this. So basically, it's saying that the first part of the string should be some type of software engineer. And then there can be various stuff that we don't care about in the middle. But the end part of the string should represent a geopolitical entity. So GPE here stands for geopolitical entity. But again, we don't want just any geopolitical entity. We want the country associated with this geopolitical entity to be United States. And so let's take a look at this string. How do we match it against this regex? Well, first, by consulting an LLM, it can tell us that .NET developer is indeed a type of software engineer. Winter Park, Florida is a geopolitical entity. And of course, the middle part will match .star. And then we're going to do retrieval. And we're going to consult an external information source to look up attributes of Winter Park, Florida. So for example, we're going to look up its country. And then we can symbolically evaluate our predicates. And based on that, we decide that there is, in fact, a match here. Okay. So we talked about the representation. Now let's talk about the learning algorithm. So as you all know, if you have some complex data extraction tasks, writing regexes can get quite annoying. And most people don't enjoy writing regexes. So instead of asking people to manually write these semantic regexes, we want to completely automate this data extraction task, again, using a programming by example approach. And as before, the idea is that the user provides a small number of examples. In this case, we need a few positive examples of strings that should be matched, and a few examples of negative strings that should be rejected. And we want to automatically generalize from those and synthesize a semantic regex that we can then use for data extraction on a much larger data set. So again, I don't want to talk about our learning algorithm in a lot of detail. If you're interested, I'll refer you to our Uppsala paper. But what I did want to kind of, again, highlight is this interplay between search and neural guidance and symbolic reasoning in the search algorithm. So as before, as in the first part of the talk, at the core, we have some sort of backtracking search. Again, this idea of top-down enumerative search. But here, rather than doing blind search, our top-down enumerative search will be guided by a large language model. And specifically in this context, given the positive examples, we use an LLM to predict the skeleton of the regex. So think of it as some sort of sketch. And then once we have that sketch, this is where we do type-directed search. So we have a type system that has a notion of subtyping. And we can use this type system to both guide the search and do systematic pruning of the search space. And furthermore, if synthesis fails, we can also use a combination of the type system and a basic form of program analysis to do fault localization, so we can identify what part of the sketch was problematic, and we can use it to do localized repair, and we can reprompt the LLM in a much more intelligent way. So the symbolic reasoning guides LLM prompting in this case. So again, quick highlight of our evaluation. So we evaluated this method on a bunch of data extraction tasks that were provided to us by a company called Sigma Computing that we were collaborating with at the time. And they actually had very interesting data extraction tasks that had both a syntactic pattern matching component to them as well as some semantic reasoning requirement. And they had a bunch of different domains involving email addresses, merchandise, log files, and so on and so forth. Okay? So to evaluate our method, we considered 3 baselines. So the first baseline is what I will refer to as regex. So here, rather than synthesizing a semantic regex, we're again learning a regex, but we're instead using a traditional regex. So this baseline allows us to assess the importance of semantic regexes as opposed to traditional regexes. Our second baseline is a purely neural approach, namely just GPT. So what we did here is we took whatever version of GPT was available at the time. I believe it was 3.5. But we provide GPT with all the positive and the negative examples provided by the user. And then given a new string in the test set, we ask the LLM, should this be accepted or rejected? Should it be matched or not matched? And our final baseline is a tool called Flash GPT. So I'm sure many of you are familiar with Flash Fill and that family of tools. So this is This comes from the FlashFill family of tools from the Microsoft Prose team. And this is also specialized for a tool that's specialized for data extraction, and it's also neurosymbolic, but it combines LLMs and regexes in a very different way than we do here. So to compare these approaches, we provide all of them the exact same input. So every tool gets 3 positive examples and 3 negative examples. And we measured relevant statistics on the test data. So what are relevant statistics? One is, of course, recall of the strings that we should extract. What % did we actually end up extracting? Another important statistics is, of course, precision of those strings that we extracted. What % are actually relevant? And, of course, if you want to look at the combination of precision and recall, the typical metric is F1 score. And as you can see from this small table, so in terms of recall, FlashGPT and our method are pretty similar, 0.83 and 0.84. They both do better than the other 2 baselines. But in terms of precision, our method significantly outperforms the other baselines, which, of course, yields in an overall the best F1 score. OK, so to recap, in this part of the talk, we looked at an application of neurosymbolic programming to textual data. And we saw how it enables flexible pattern matching by combining the power of traditional regexes with large language models to do more semantic reasoning about textual data. OK, so in the last application domain that I'm going to talk about, we'll consider a more futuristic application domain, namely robotics. And again, if you would like to learn more, this part of the talk is based on our POPL'24 paper that was led by my student Noah Patton, who is co-advised with a robotics faculty at UT. OK, so I always like to give a motivating scenario. So for this part, suppose that you bought a new robot. I told you it was going to be more futuristic, but let's say you have a new robot. This robot has been trained to do certain tasks, but not others. And now you want to teach the robot some new task that you in particular care about. So for example, as you can see from this image, I'm a big coffee drinker, so I always have dirty coffee mugs sitting around in my house. So I would personally like to teach my robot to collect dirty coffee mugs lying around in my office or my house, right? So there's a common approach to doing this in the robotics community. This is a common approach for human-robot interaction is this idea called learning from demonstration, or LFD. And the idea here is that the user provides a physical demonstration to the robot, and the goal of the robot is to generalize from the demonstration and learn a policy that can be used to perform similar tasks in slightly different environments. OK, so of course, there's a lot of work on LFD in the robotics community. We're clearly not the first people to talk about it. So for example, you might have heard of approaches like behavior cloning, which is a type of imitation learning, or there's this idea of inverse reinforcement learning. So there is a lot of work out there. But if you reflect on all of those, I would say that one common theme across all the existing work is that they represent the policy using a purely neural representation. And I don't mean to undermine any of this existing LFD work. There's many settings where these ideas work really, really well. But there are also some areas where existing techniques don't work very well. And a typical example of such domains is what roboticists call long horizon tasks. So in a nutshell, long horizon tasks are these kinds of tasks that require the robot to perform a sequence of interrelated actions over a longer time horizon, right? So existing techniques don't do very well with long horizon tasks. And additionally, they also have the usual problems like lacking interpretability and requiring significant amount of data, which in this context means that the user needs to give lots of demonstrations, which can be tedious. So to address these shortcomings in the context of long horizon tasks, we developed a new neurosymbolic approach called PROLEX. And here, rather than having a purely neural policy representation, we instead represent policies in a neurosymbolic DSL. And as you saw in the other parts of the talk, here we're going to be using neural components for perception as well as motion planning. And we're also going to use symbolic constructs like conditionals, loops, and so on to capture repetitive aspects of the tasks and for doing better decision making. So going back to a similar example to what I was saying earlier, so let's consider the task of collecting dirty sheets from around the house. So you can express a policy for doing this in our domain-specific language. So as you can see, for this application domain, we have this imperative language with a bunch of nested for loops, assignments, and so on. And if you stare at this for a second, you will see that there's this atomic command called scan for a certain type of object. So this is allowing the robot to locate objects of a specific type. And this is, of course, used for perception, and it's implemented using a vision language model. And as you can see here, we also have atomic commands like open, grab, close, and so on. These also correspond to pre-trained neural networks for basic skills that pretty much every robot needs to be able to do. And of course, these are all composed together using our symbolic constructs like sequencing, loops, conditionals, and so on. So again, that was the representation. Now let's talk about the learning task. So remember that here we're trying to do learning from demonstration. So the input to the learning algorithm will be a demonstration. And the demonstration, we represent it as a pair. One part of the demonstration is a trace. So it's basically a sequence of atomic actions that have some externally visible effect. For example, open, put in, and so on. And recall that the demonstration is also, of course, performed in some environment. So therefore, the other part of the demonstration is some representation of the environment in which that demonstration is performed. So given these two inputs, the goal of the learning algorithm is to learn this robot execution policy. So again, I don't want to talk in a lot of detail about the learning algorithm, but once again, I did want to highlight the synergy between LLM-guided search and program analysis here. So as before, our top-level algorithm is based on this top-down enumerative search, but here we use LLM guidance in order to provide common sense priors during the search process. So what do I mean by that? Well, let's say in our partial program, we have a statement that says place some object in a laundry bin. And let's say it has some unknown conditional that we're trying to synthesize. Well, if you consult an LLM, it can tell you that you're probably much more likely to check a property like, is this object clean or dirty, as opposed to some other property like, is it wrinkled, does it have a certain texture or color? So here, by using LLM guidance, we can get common sense priors about the real world in which the robot operates. Now, it turns out that even more importantly than LLM guidance, a huge requirement for making this work that we found is to use program analysis. So what we do here is, given a partial program, we use a form of abstract interpretation to over-approximate all of the traces that could be generated by that program. And if we find that the user's demonstration is not among those over-approximated traces, then we definitely know we're at a dead end, and we can, again, use it to do systematic pruning of the search space. So program analysis for the win once again. So again, some highlights from our evaluation. So we implemented this in a tool called Prolex, and since our target is long horizon tasks, we evaluated it on an existing data set called behavior. So this is a data set put out by the Stanford robotics folks, and we chose this data set because in a prior paper, they showed that existing imitation learning or reinforcement learning techniques don't work for these kinds of long horizon service tasks that are performed in household environments. So existing neural techniques perform pretty abysmally in this setting. They basically cannot do any of the tasks. And using our method, it's far from perfect, as you can see, but what we did find is that given a 2-minute time limit, our tool was able to synthesize a program consistent with the demonstration for 80% of the benchmark. So you can think of it for 80% of the benchmark, synthesis succeeds. But of course, if synthesis succeeds, it may or may not produce the ground truth. And we find that among the programs where synthesis terminates, 81% of the learned programs actually correspond to the ground truth and generalize to other environments. So overall, the success rate here is around 65%, so there's significant room for improvement, but still, we see a big improvement over purely neural techniques. Okay, so in this last part of the talk, I'm going to reflect on a cross-cutting concern across all of these different application domains that we looked at, and I want to talk about how we can ensure trust in neurosymbolic learning. So first, what the heck do I mean by trust? Well, what I mean is that in all cases, the synthesizer, if it doesn't time out, it returns you a program, but how can you as the user have any confidence that it's actually returning or synthesizing the program that you want? One solution to this problem is you can go ahead and ask the user, please go ahead and inspect the program, give me a thumbs up or a thumbs down. And I would argue that this is probably easier than inspecting the weights of a neural network, but I think we can all agree that this is suboptimal, right? It's not feasible for most end users who may not have programming expertise or who may not be familiar with the DSLs that we're using. So a better solution to this problem is this idea of active learning. And the idea behind active learning is rather than asking the user to passively label some data, you interactively query them. You reason about what's the most informative input, for example, for the user to label. And you interactively query the user until you're very confident that you've converged to the right program. So for example, going back to our image editing setting, rather than asking the user to passively label a bunch of images, the synthesizer can internally reason what's the most informative image in this data set, and they can ask the user to label that particular image as opposed to some random image, right? And the user provides an answer, and based on the user's answer, we're going to refine our hypothesis space. And we want to keep doing this until some termination criterion is reached, for example, until all programs are observationally equivalent on the inputs that we care about. And very importantly, when you do this active learning, the goal here is you would like to do this in a way that minimizes the number of rounds of user interaction, because if you ask lots of questions to the user, that's not particularly helpful. Now, again, we're not the first people to talk about active learning in the context of program synthesis. There's actually lots of great work from the PLDI, UPSLA, POPL community on active learning for program synthesis. I highlighted some of the prior work here. But one kind of common theme among all the prior work is that they target the traditional purely symbolic program synthesis setting. And what that means is that if you apply them to neurosymbolic programs, they're not going to account for possible mispredictions of neural constructs. And as a result, they may end up erroneously eliminating the desired program, meaning that synthesis will fail. So this is probably not obvious, so let me illustrate how that can happen through a concrete example. So a very simple example. So suppose that I want to synthesize a program for cropping all of the cats in a given photo, right? And you can achieve this task using this very, very, very simple program in our DSL that looks like a one-liner that looks like this. If it's a cat, then apply a crop action. And now if you query the user and ask the user to label this data, of course, they're going to tell you that this is the desired output. Right? So far, so good. But here's the problem. Recall that this construct, this predicate is cat, is actually implemented using a neural network. In fact, it's implemented using two neural networks. To evaluate this, you first need to do image segmentation. And once you do that, you also need to do image classification. So if either of those has a problem, it's entirely possible that you may misclassify some of the objects in the image, right? So for example, for this cute picture here, let's say that the object classifier gets confused by the snow on the dog's nose. So let's say it ends up misclassifying the dog as a cat. So instead of thinking there's a cat and a dog in this image, we now think there are actually two cats. Okay? So what's the problem? So recall that during active learning, we're going to evaluate each program, and we're going to check if if I execute this on the input labeled by the user, I want to check if it actually matches the user's output. But now, if I execute this program on this image, I'm going to end up with two cropped images because we think this dog is also a cat. And obviously, this is not going to match the user's answer. And as a result, we think that this program is wrong, even though this is actually the desired program that would have worked on most of the images in the user's data set, but we're going to end up eliminating it, and which means that learning will completely fail. So in our recent work, the question that we asked is, how do we ensure that we return the correct program to the user, even when these neural components can have mispredictions? And the key idea that we're exploring is to leverage a new type of semantics called conformal semantics of neurosymbolic programs. And the idea here is to build on top of this rich literature on conformal prediction in the machine learning community. And if you're not familiar with conformal prediction, in a nutshell, the idea is that you want to return a set of predictions rather than a single prediction. And in doing this, you want to train the neural network in such a way that the ground truth is going to be contained within this prediction set with very high probability. So you can think of it as you have a different optimization objective that emphasizes correctness rather than precision. So in our ongoing work, we are exploring this technique that allows you to efficiently propagate conformal prediction sets through neurosymbolic programs, and does this in a way that takes the user's answers into account. And building on that conformal evaluation method, we are working on an active learning algorithm that leverages conformal evaluation to select the most informative queries to ask to the user. And ultimately, the guarantee that we get is upon convergence, we want to make sure that the program that's returned to the user is likely to be the desired program with very high probability. So unlike a lot of formal methods techniques here, we don't get hard guarantees. We can't say with 100% confidence you're going to get the desired program, but still you get this probabilistic guarantee, which I would argue is better than having no guarantee at all. And furthermore, this probability is a value, it's a knob that can be controlled by the user. Okay, so kind of to wrap up, I'm personally very excited about neurosymbolic programming. I think it really opens up new avenues compared to just purely neural or purely programmatic approaches. And by, as I kept emphasizing throughout the talk, by using neural networks, we get the ability to deal with messy real-world inputs like images and unstructured text. But at the same time, by using programming languages, we get modularity, we get interpretability, and we get more data-efficient learning. And I'll conclude by talking about a few directions for future work, if any of you in the audience are also interested in joining this neurosymbolic program synthesis area. So one interesting direction is, as I kept emphasizing, in a lot of the work that we've done in my group, the neural components in the DSL correspond to pre-trained neural networks. But one interesting idea is that can you actually co-learn the symbolic representation and the neural representation, for example, by doing fine-tuning on the neural networks, especially if you can't find a good matching program. Another interesting thought here is, again, as I kept emphasizing, there is a lot of expertise on, there's a lot of emphasis on DSL design, and this requires a lot of human expertise. And the idea here is that instead of relying on humans for DSL design, can we semi-automate this process, for example, by coming up with new program abstractions, or maybe slightly modifying the existing semantics of constructs in order to adapt to slightly different domains? And last but not least, I think there's also this very important question is how do we account for uncertainty when you execute neurosymbolic programs? And I think this is especially important in safety-critical settings like robotics. So for example, by explicitly reasoning about uncertainty, you may be able to detect when the robot is about to do something unsafe, and then you may fall back on a more conservative course of action, or for example, ask the user for help. And last but not least, I do want to thank all of my collaborators. Unfortunately, I didn't get a chance to fit all of them on the slide, but I did especially want to acknowledge my students who led these projects, Celeste, Jocelyn, and Noah, as well as 3 key collaborators, Osbert Bastani from Penn, who works at the intersection of ML and PL, my colleague Greg Durrett at UT Austin, who works on natural language processing, and my colleague Joydeep Biswas, also at UT, who works on robotics. So that's my talk. If you have any questions, I'm happy to take them.
Okay, folks, please come on up to the microphones and make sure to introduce yourself.
I can hear you, Manu. If you want, I can repeat the question for you.
Okay. Use this. Hi, everyone. Manu Sridharan, UC Riverside. Really cool talk. One thing that was going through my head is all this buzz around like agentic AI, and it seems to be almost the inversion of what you're doing, right? Because there it's like you let the large language model run the tools, and in a lot of your synthesis techniques, you're kind of running the large language model as a subroutine. So I was wondering if you would kind of agree with that characterization and kind of
That's a great observation. Yeah, I hadn't actually thought about it in that way, but when you say it like that, yeah, it seems like the inversion of agentic methods.
Yeah, and as a PL person, I like your methods a lot more. But I was curious if you've like thought about whether the agentic stuff kind of fits into this agenda also.
I guess one way to look at agentic methods is that you're composing different LLMs that are good at different things. So in some sense, I think you can view them in a more uniform framework. But it's a really interesting observation. Yeah.
Cool. Thank you very much.
Sure.
Hi, Xiaokang Chiu from Purdue University. Thank you for the excellent talk. So I think we all agree that neural approaches and symbolic approaches are complementary. But I think both fields are rapidly evolving, and what we consider weakness or strength can be no longer the case next day or next month, right? So we may consider that language models are good at recognizing cities, but not good at counting. But maybe next month we have a stronger model, or for symbolic approaches, we may consider some tasks are too big to search with today's algorithms, but next day we have a better algorithm. So I just want to hear your thoughts or experience on building neurosymbolic learning algorithms on top of these ever-changing
I think you have a good point, and I do think we need to be very cognizant of the fact that LLMs are constantly improving. But I think I did highlight some of the things that I tried to highlight are universal, and there are problems that are going to remain no matter what neural method that you look at. At the end of the day, these things get like bigger and bigger, so it's like interpretability is definitely going to remain a problem, verifiability is going to remain a problem, and so on.
Yeah, thanks.
Sure.
Check. Okay, hi, this is Ruiji from Peking University, and I'm pretty curious about the definition of equivalence in your slides, because you mentioned observational equivalence, and also in active learning we need to check the equivalence of users' response and the program. Yeah, but I guess a pretty significant difference here is that, for example, for the case of image processing, the user's response may have some noise, and also the output of the neural network will have some noise, right? Because if we want to crop up image, then there are many different, slightly different ways. So I'm curious about whether we need some, for example, new definition of equivalence or new semantic approach to tolerate such kind of noise.
So you brought up two different sources of kind of ambiguity here. One of them is like the one that arises from the neural network mispredictions, which is what our, like the last part of the talk aims to address. But for the other thing that you talked about, namely that there are many ways you can crop the image, I absolutely agree with that. But in this image search and editing work, in order to deal with that kind of noise, what we basically allow the users to edit the image through some kind of like graphical user interface where it basically like shows bounding boxes, and then the user can only apply a crop action to that bounding box area.
Oh, that makes sense. Yeah, thank you.
Sure.
Hi, I'm Bungjin from KAIST, and I was thinking what would be the ultimate application when this neurosymbolic AI is really realized. And I think the application would be the automotive, like self-driving cars. And the really difficult problem to applying this neurosymbolic AI technique to automotive is that it's not really easy to encode our knowledge of driving into this DSL. And the second problem is the driving knowledge always is evolving. Like, for example, in Korea, there was kind of really messy situation, like, can I turn right on the green light? And the law changes like 3 times or 4 times during the past 2 weeks. So yeah, it was really crazy. And it's really easy to update the LLM part in the neurosymbolic system, but but if, let's say, we somehow encoded our knowledge into DSL, but it's not really hard. It's hard to update some part in the DSL automatically when we have a new knowledge. So I want to hear your thoughts about this problem.
So can you state it as a question? You said you made a lot of points there, so yeah. I was like not quite sure what's the part that you want me to address. I mean, for example, I think we can have a lot of discussions about what's the ultimate, success, like it's like asking when do we think we did AGI, right? So I don't know what's like the equivalent for neurosymbolic program synthesis, but it will be helpful if you can kind of distill your question.
The first thing I think there's a tension between what part should be an LLM part or what part should be the symbolic part. So at least I want to hear your experience of designing those parent.
That's a great question. There is indeed such a tension. So basically, what we do is we ask the question when you're designing a DSL, for example, in the image context, what are they good at doing and what are they not good at doing? And you basically the existing methods are good at image segmentation and object classification, so you use them and then you basically based on their outputs, you try to glue everything together using symbolic constructs. So I think that's an evolving thing rather than a static thing. So yeah, it has to do with the earlier point I think that Rui was making, which is that LLMs are constantly improving, and that means that probably the design of these DSLs also needs to improve.
Okay, the second point was?
I think let's do one last quick question, actually. No.
No.
All right. Really nice talk. So I'm actually thinking about the LM and the train of the MCP. So there are more and more effort of connecting LM with various different application interfaces. And I want to see your thought of how this train will affect your approaches, because I see the kind of the bottleneck to the scalability is the DSL and requiring to design DSL if there are more new agent gets new interface application gets connected to LM agent, and hoping to automate tasks, it would be requiring to design like update the DSL or something. So
I think you're asking a pretty open-ended question, so maybe it will be more productive if like we take this offline and have a longer conversation.
Okay, let's all thank Işıl again for a fantastic talk.